All right, everyone. It's 10:30. I think we can look at some scenarios in the workshop. So we'll not go through everything because it's a lot, and then it's really just you playing around with the PhET simulation. But we'll just look at some examples. So say, for example, for the first one, um, sort of the idea behind this is seeing a pattern for when the beam is balanced and therefore you have equilibrium. So the first example shown here is when a 5 kilogram object, let me just make this bigger. Yeah. So you have two 5 kilogram objects here. One is placed on the right 1 meter away from the support or pivot point, and the other is also 5 kilogram object placed 2 meters away from the support. All right. So we're given the masses. You have to calculate the weights, and we know that weight is equal to mass times gravitational acceleration. So it's not the kgs that we need, it's the force, because torque is equal to moment arm times the force. So therefore, we need to find this force is given by the weight force. Recall, weight is equal to mass times gravitational acceleration, where G is equal to 9.8 meters per second squared. Or to make things simpler here, we can just use G is approximately 10 meters per second squared. So we're just multiplying the mass with a factor of 10, and that makes it simpler. And that's why the weight of the 5 kilogram mass is 50 newtons. Okay, it's 5 kilograms times 10 meters per second squared. So for the mass on the left, you have 50 newtons for the weight force, right? So this is the weight force, 50 newtons times the lever arm. Lever arm is the distance between the weight force and the pivot point, which is 2 meters. That gives you 100 newtons. And on the right, you have your 50 Newton force, the weight force, 50 Newton weight force because of a 5 kilogram mass. And the lever arm is 1 meter. The distance between your weight force and the pivot point is 1 meter. So you can see here it's not balanced because the torque, the anti-clockwise torque is not equal to the clockwise torque, and that's why it's not balanced. As opposed to in this scenario here, yeah, you can see that the torque, force times lever arm, force times lever arm is the same, and therefore you have a balanced beam in the second scenario. So you can observe that if the weight force is the same, then the lever arm, lever arm should also be the same to give you the same amount of torque. Right, and so you can do examples here, but let's just take one hypothetical scenario. For example, I have a for example, I move my 5 kilogram mass and I put it 1 meter away on the left. So that's my 5 kilogram mass, 1 meter away. If I took a 10 kilogram mass and I placed it the same distance away from the pivot point, do you think this will be balanced? Here, a 5 kilogram mass 1 meter away from the pivot and a 10 kilogram mass 1 meter away from the pivot. No, right? Obviously, they're at the same distance relative to the pivot point, but the one on the right is heavier. So obviously, this will tip over. So where do you think I should put my 10 kilogram mass for the beam to be balanced? Well, you can, yeah, we can work this out. So this one will give you a 50 Newton weight, and this one will give you a 100 Newton weight force. If you work out the torque on the left, a torque on the left is 50 Newtons times 1, lever arm is 1. And the torque on the right is 100 times 1. Yeah. That will give you 50 Newton times meter. That's obviously not equal to the weight force 100 times the lever arm of 1. Yeah, this is 100 Newton meters. So obviously they're not equal, they won't balance out. So where should I put the 10 kilogram mass? Okay, if we put it at 2 meters, so that's your 5 kg mass with a weight of 5 Newton. Right, so we know this is 50 Newton times 1 will give you 50 Newton meter torque. My pen. 50 Newton meter torque, right? So if I have a 10 kilogram one and I place it at 2 meters, so that's a force, weight force of 10 Newton for a 10 kilogram mass. That's 100 Newtons for a 1 kilogram mass. Okay. Where should I place it so that I also have 50 Newton meter torque? Yeah, very good. Yeah, thanks for, you corrected yourself there, Roxana, which is good. Because if you place it at 2 meters, then you're placing the heavier mass farther away, and it will actually just pull this downwards. And if you do the calculation for that, if you put it at 2 meters, that will actually give you 200 Newton meter torque, which is not equal to 50 Newton meter. So you have to put it halfway because the mass is twice. So if you put it at 0.5, instead of putting the 10 kilogram mass there, should put it here, and that would balance out. So if you go to the PhET simulation and you put your 5 kilogram mass at 1 meter, notice if you put, obviously if they're in the same distance, they're not balanced. If you put the 10 kilogram mass at 2 meters, they're not. But if you put it at 0.5, then they're balanced out, right? Okay, so the force given by the weight and the position of that force are both important in this case. Okay, so I will let you do through part 1, finish that on your own time. And let's look at some examples for part 2, right? Are you happy to move on to part 2? Do you think? Yeah, okay, good. All right, so for part 2, what's part 2? Okay, for let's answer this question. So what do you notice about the Newtons times meters for your balanced masses? So if you fill out the table, so balanced masses is the one on the right. Okay, if you fill this out, you notice that the Newtons times meter should be the same, meaning the torques on the left side of the beam should be equal to the torques on the right side of the beam for the beam to be balanced. Okay, so that's the answer for that question. For the second part, you're given mystery masses. You don't know how much each one weighs in kilograms. Of course, just multiply that with 10 and you know the weight of that object. But you are given, okay, so part 2, it's this balance lab here. So again, it's useful to put the level and then use a ruler. And we don't need the support, so remove the support by toggling that button. So you have here your mystery objects. They're here on the right, but you can also access fixed masses. Okay, so you have bricks with fixed masses, and you have the mystery objects here. So let's try to do mystery object 1. So say, for example, I put the mystery object at 1 meter because it's easy to multiply with 1, right? If your lever arm is 1. Yeah, so obviously the beam goes down like this. So we need to be able to balance that out using our fixed masses. And using our fixed masses, we can sort of figure out what the mass of this object is. So did anyone do this during the workshop early, and were you able to sort of find out what's the mass of this mystery object 1? So any guesses for this mystery object 1 before we look at how we determine the mass of this? No? No wild guesses? Right? Okay. So let's try to see. Maybe I'll try to choose my 10 kilogram mass because it's easy to multiply something with 10. So for example, maybe I use this 10 and I try to put it at 1 meter. Same distance as where my mystery mass is. So the beam isn't balanced. So that means that the mystery object shouldn't be 10 meters, right? 10 kilograms. The mystery object it should be heavier. It's heavier than 10 kilograms because it's still weighing down on the beam. All right, so should I move this 10 kilogram mass farther than 1 meter or closer than 1 meter to try and balance out the right-hand side? Yeah, so if you try to put the 10 kilogram mass closer to the pivot point, so it cannot offset the imbalance there, but you try to put it farther away, say 1.5, still not balanced. Okay, try to put it at the extreme, and you see there, yeah, okay, so it's balanced. So that means with a 10 kilogram mass and the lever arm of 2 meters, that balances out the mystery object A that has a lever arm of 1 meter. Okay, so what do you think is the mass of the mystery object 1? Yeah. So it balances when 10 kgs is at 2 meters. It means that the mass of object A should be twice the mass of object B because the lever arm of 10 kilograms is twice the lever arm of object A. And torque equals mass times lever arm. So that means the lever arm, the mass of object A should be twice. So it should be 20 kilograms, right? So that's how you do part 2. Yeah, you can do the same thing for mystery object B as well. You use these bricks with fixed masses, or you can also use the people. They also have fixed masses, but I would suggest the bricks because you have more masses to play with. All right, is that okay? Do you want to look at one more mystery object, or do you want to move on to the third part of the worksheet? Yeah, no preference. Okay, maybe we can move on to the third part because the second part is just repeating the example we did with mystery object A, just trying to balance things out. Oh, maybe before we move, let me just work that example out mathematically, because it's easy when the lever arm is just doubled, then the mass should also be doubled. But when it's not a clear-cut doubling, then or halving, then we need to use the equation for torque. So for here, we put the mystery objects at at the 1 meter lever arm. So your lever arm, so you have here the weight force for your mystery object. Your lever arm is measured from the pivot point and the perpendicular distance. So let me just use a different color. Right, so that's your pivot point. This is your weight force. Your lever arm, maybe I'll make that bigger. Yeah, your lever arm is that distance that's perpendicular to your force and passing through the pivot point. So that's the lever arm is equal to 1 meter for the mystery object on the left. Yep, and then correctly we placed the 10 kilogram mass. Where was that? $10 kilogram mass was here. Yeah, so you have these weight force is equal to 10 newtons. That balances out the object. To find the lever arm for this weight force, okay, extend your weight force, and it's the distance that's perpendicular to your weight force and passing through the pivot point, so that's 2 meters. Oh, sorry, the weight force is 100 newtons. Right. So when you calculate the torque, yeah, the torque due to the 10 kilogram one, torque is equal to your lever arm 2 meters. 2 meters times 100 newtons, that's 200 Newton meter. Right, and the lever arm on the torque on the left is the lever arm 1 meter times the mystery weight, okay? And they should be equal. Right? Okay, 1 meter times you don't know, and this should be equal to 200 Newton meter. Okay? Because the torque on the right should be equal to the torque on the left. So therefore, your weight should be equal to 200 newtons. And that gives you a mass of 200 newtons divided by 10, the gravitational acceleration. So that should be a mass of 20 kilograms. Right, so you can use this procedure if it's not, the relationship is not a direct doubling or the direct halving, then you have to work out the equation torque is equal to force times lever arm. All right, but otherwise in our example here, it's directly doubled. So the lever arm is also doubled, and it was easier to find that. Okay, let's just do level 1 of this game. And we'll put the ruler here. Okay, so where should we put the 5 kilogram mass in order to balance this beam out? There's a 5 kilogram mass at 1.75 meters away from the pivot point. Okay, so where should we put this 5 kilogram mass on the right to balance it out? Yep, it's the same mass. That means the same weight force. So you should put the 5 kilogram mass at the same position. Yeah, if you do the check, then it's balanced out. All right. You have a 10 kilogram mass on the left at 1.75 meters liver arm, and a 5 kilogram mass on the right with 1.75 meter liver arm. Right. What will happen in this scenario? Is it the top left? Where is it? This one? Is it this one or the right scenario? Left, right? Obviously, they're placed at the same liver arm. They have the same liver arms, but one is heavier. So obviously, the heavier one will tip the beam to the left, right? Okay, now here you have different masses, 20 kilograms and 40 kilograms. Where should we put the 40 kilograms? How should you adjust the liver arm in order to balance this beam, right? Okay. Yeah. Okay. Put that at 1 meter because it's heavier. Yeah. Very good. Yeah, it's heavier twice, 2 times heavier. And so the liver arm should be half. Good. Yeah. Here, what's the mass of this 20 kilogram one? Okay. Let's try to find the mass. I don't know. I think this is randomized. So I think if you start the simulation and you reset it, maybe it will give you different answers. But say, for example, I put that there. Oh, this is no challenge. Because the intuition is like put it in the same position, right? And if it balances out, then you know what the mass is. And so this is not challenging at all. I guess that's why it's level 1. Yeah, so it already balances out right away. So you already know it's 20 kilograms. Yeah, because it's in the same liver arm. So that means the weight force should be the same and the mass should be the same. Yeah. All right, here, yeah, you have 5 kilogram and 10 kilogram masses, and they have the same liver arms. What will happen? Is it this the left, the middle one, or the right one? Yeah, the challenge will be like a bit later in level 3. I think you would want to do level 3. This is probably not so much challenging. Yeah. So obviously you have the same liver arm. Yeah, the heavier one will tip the balance to downwards. And let's see this last one here. Right, you have unknown mystery object again, and it's at 0.25 liver arm. And you have a 30 kilogram rock. Usually my intuition would be just to put this object in the same distance so that they have the same liver arm. And if it balances out, then it's easy. They have the same weight, therefore they have the same mass. But in this case, they don't, right? They don't. So then maybe I'll try to double the distance, because then that means if they balance each other out, then I can sort of figure out, right? Oh, and if the liver arm is doubled, it's level, it's balanced out. So what do you think is the mass of this mystery object? $15 kilograms. Okay, let's try 15 kilograms. Oh, it's not 15 kilograms. Okay, so that was 15 kilograms is half of the 30 kilogram, right? And then there's there a doubled answer, so 60 kilograms. Okay, let's try to see 60 kilograms. Yeah. So 60 kilograms, because 60 kilograms multiplied with 0.25. Oh, so let's do that in weight. So 60 kilograms, that's 600 newtons. For the weight force, multiply that with the lever arm, 0.25 will give you 24. That's multiplying by 4. So that will be 150 Newton meters. Okay. And 30 300 newtons times 0.5 will also give you 150 Newton meter. Okay. A little bit tricky there, but good. All right. Oh yeah, you actually corrected yourself, Oksana, so that's good. Okay, and if oh yeah. And yeah, if you want, you can go to level 4, which is challenging bit where you have more objects now. Yeah, but I'll leave that to you to do for extra practice. I think we're nearing 11 o'clock. So are there any questions at all about the workshop or the lecture or anything else? Yeah. So today we looked at torques, how to calculate the torque, and for that you need to draw the free body diagram and determine the lever arms. We balanced out the torques. Next meeting we will still look at torques, but looking at a more other examples, but it's still about torques. And now we will combine net force and net torques in the next lecture. And I forgot to announce this in the beginning of the lecture. Maybe the announcement will come out soon on stream, but the mid-semester test is coming up next week. The exact date and time will be announced on stream soon. So in the review workshop this week, I will go over some practice problems in preparation for the test. The practice problems, if you're interested to look at them now, they're on stream in under workshop 10. So scroll towards the bottom of the stream page. Maybe I'll stop sharing. Scroll towards the bottom of the stream page, and then you will see their practice problems for the semester test. I'll go over the solutions of those during the review workshop on Friday from 1 o'clock. But yeah, so any questions for now? At all? Right? I think. Okay, good. So I don't see questions in the chat box, and thanks, Oksana, for the response. So I wish you a great day, and I'll see you on Friday for another torques workshop. Right. Oh, what will that mid-semester test be? Everything from week 1 to 5? Yes, it will be until torques. So it will be until today's lecture. Okay, cool. All right, I'll see you on Friday. Bye, everyone. Stop recording.